I'm here watching the sixth game of the World Series as I'm trying to put together this screencast, so I might be a little distracted. All right. Um, so, the one thing I want to make sure that you folks have a clear understanding of is that the plasma membrane's main job is to create a different set of conditions inside the cell than exist outside of the cell. And the reason that's important is that you're going to have a whole bunch of chemical reactions occurring in this area in here. And in order to have the right conditions for all those chemical reactions, you need to be able to maintain a certain constituency in here. And if it's not that way, then you won't be able to have those reactions happen properly. And of course, out here in the extracellular fluid, the area outside of the cell, there's all sorts of fluxes and changes of the environment that's going on around here. And so the internal environment needs to remain the same while the external environment goes crazy. And we've heard this term before with it as homeostasis. That's maintaining a constant internal while the external changes around you. So homeostasis, it's one of those unifying characteristics of life. So how does it do that? Well, how does it control what goes into and out of the cell? Particularly, as you know, this is a fluid model. And because it's fluid, there will be these gaps that open up. They're tiny little gaps, but they're going to be gaps nonetheless, which means that this membrane is not a sealed membrane. It is a membrane that we refer to as being a selectively permeable membrane. And by the way, I really prefer the term selectively permeable as opposed to a term that some teachers and some textbooks might use, which is semi-permeable. Selectively permeable says a lot more because it truly does select what goes into and out of a cell. Semi makes it sound too passive. Okay, so we have a selectively permeable membrane that exists, which is what not only the plasma membrane, but all the membranes inside the cell are selectively permeable. All right, so let's back up a little bit, though, before we get into this concept. Once we've established here that the cell needs to maintain a constant internal environment, we need to have a bunch of terminology in your brains before we move too far. So I'm going to actually open up a new page here. Okay, the first concept is an idea called molecular motion. And you probably recall from chemistry this concept, and that is that if you even have something like a solid block of metal, that the reality is that the molecules or the atoms that make up this chunk of metal are constantly moving. Now they're moving much less in metal as compared to, say, a liquid, right, where they're moving a little bit more and they're more spaced out. And then even further, if it's a gas, then they're really cruising around at quite a high rate of speed. But the bottom line is that you always have this inherent molecular motion. It's not like these things have engines associated with them. It's just that it's part of the energy of every atom that exists in every piece of matter in the universe. Now, as a result of molecular motion, if I have, let's say, a bottle of perfume over here, and I take off the top and it's sitting here, and this perfume is hanging out here. Let's just say it's I know perfume is not red, but that's what you get. And eventually, you should know that perfume is something that evaporates incredibly quickly. So, and because there's molecular motion associated with it, when it evaporates into a gas form, it is highly dense right here around the perfume bottle. And so we have a high concentration, and I'm just going to denote that with the brackets for concentration. You guys remember that probably from chemistry too. H indicating high concentration. So a high concentration of these molecules of perfume hanging out right there over the opening to the bottle. And that means we also have a very low concentration. In fact, we have none of molecules that are hanging out over here, molecules of the perfume. So because there's molecular motion, these things are going to spread out from an area of high concentration to an area of low concentration. So they're going to start moving down what's called the gradient. And eventually, let me just sort of circle this. I'm going to do select this whole thing, copy this. So eventually what you could imagine would happen is because of the molecular motion, inherent molecular motion, eventually all this stuff is going to disappear. It'll all evaporate out. Maybe there'll be a little bit left at the bottom. Okay, but these things will have diffused so that there's no longer an area of high concentration and an area of low concentration, particularly if I decide that I'm going to stick the cap right back in the ball there so that nothing more can leak out. So it's going to be evenly distributed. That doesn't mean that the molecules have stopped moving because you reach a dynamic equilibrium where they're moving around. Dynamic means constantly moving. But we certainly lose this low concentration now because all those molecules have evenly distributed themselves or diffused throughout the entire area. Oh, wow. Kansas City just scored a couple more runs. Now it's 4-0. Sweet. I want a game 7. All right, so okay, so again, there are a couple terms I just used there. One was dynamic equilibrium. Oops. So we have equilibrium in that there's no high or low concentration in this space here, but all these molecules can move around, and they're moving around in random directions. And as soon as you have a local area, let's say all of a sudden a whole bunch of molecules here come in tight, well, diffusion is going to force those guys to move away from there, and as a result, you're going to lose that area of concentration, high concentration, as they get distributed throughout, right? So the dynamic equilibrium is important. In fact, one way to think about dynamic equilibrium is think of the hockey game. You should at any one time have 12 players on the ice, the 5 ice players plus the goalkeeper. And but if you substitute, which you can do, you're going to always move one player off the ice as you move on another. So there's always going to be 12 players on the ice, but it might be a different set of players because they're cruising around getting tired. They need to be replaced. So that's really what we have going on here. Okay. Oh, yeah, and then I used the term diffusion. And diffusion is the movement of molecules from an area of high concentration to an area of lower concentration down the concentration gradient. Okay? So movement of molecules down the concentration gradient, meaning high to low, from areas of high to low concentration. I'm sure that's a term that you've heard before. So let's see how this connects to our discussion of cells. Let's go to another page here. Imagine this. We have a beaker. Oh, there's a couple more terms that I'm going to cover here. We have a beaker, and in this beaker there's a solution of water and, say, salt. Okay, so by the way, in that case, the salt is the solute, while the water is the solvent. Okay, so solvent, and then we also have salt, NaCl, and that's the solute. Okay, so that means, and if it's a solution, then it is evenly distributed. The salt is evenly distributed throughout that solution. Okay, so salt, solvent. Salt is the solute, solvent is the water. So let me go ahead and select this thing up. And I want to create a specific situation here. Let's say in this case, my water, I have it at 98% water. And that means my solvent, which is in this case the salt water, is only 2%. Okay, so I've just told you what the concentration of my solution is. But inside this solution, I want you to imagine there's a cell. And in this cell, it mostly consists of water, but in this case I'm going to say it's 95% water and only 5% salt. Now, it isn't really salt, it's whatever is dissolved in the cell, which includes organelles and sugars and all those kinds of things. So whatever the solute is, it's 5%, but I'm just going to say it's sodium chloride just to make things easier for us. And in this case, don't forget that there's a selectively permeable membrane that surrounds our cell. And I want you to imagine that the selective permeability is such that water can go through, but that the salt can't go through. So it can't go in or out. So it's impermeable to salt, but fully permeable to the water. Now this is going to be a very important thing because there's a process, there's a term called osmosis. And osmosis is the movement of water through a selectively permeable membrane. And that's exactly what we have going here with this, let's say it's a red blood cell hanging out here. Okay? So if the salt can't move, but the water can move, and we understand the concepts of diffusion, which say that a substance is going to move from an area of high concentration to an area of lower concentration, notice that in this case we have a high concentration of water outside the cell as compared to inside the cell. Now the cell can't help it. Water is going to move into and out, and it can't really control water movement. It can only control the solvent, or the solute movement. So in this case, the water is going to go from an area of high concentration, which is outside the cell, to an area of lower concentration, which is inside the cell. And I'm going to show that movement with this blue arrow here. Okay, so the blue arrow indicates the movement of our water. Now, of course, in the same way that if you blow air into a balloon, it causes the volume of the balloon to expand, well, the volume of the cell is also going to increase. So this red cell that you have in here is going to increase in size, and it's going to become bigger as more water enters into it. So there's I'm going to show the water going in. At some point, it's not going to be able to take any more water in because either the interior of the cell is diluted to, the exterior of the cell, the extracellular space has increased in its concentration of sodium chloride because it's lost water, or the dilution that exists inside the cell will have increased the concentration of water relative to the solute inside the cell. And so it'll come to a dynamic equilibrium once again. Now, here's a couple of terms that I need you to throw at you when you have this situation. In this case, the cell is in a solution that has a higher concentration of the solute than the solute. Wait, what did I just say? I got distracted by seeing a double on TV. Okay, there's a higher concentration of salt water inside the cell than outside the cell, and as a result, that makes this cell in a hypotonic solution. Tonicity means concentration. Hypo means a lower concentration when we're talking about the solute. So it's in a hypotonic solution. And when a cell expands as a result of being in a hypotonic solution, we have a term for that. So cell volume increase, that's called cytolysis. Cytolysis. So whenever a cell is placed in a hypotonic solution, water will go into the cell, which will lead to cytolysis. Now, if you have an extreme difference, let's say the water is sort of like 80% water, or I'm sorry, the solution around the cell is 80% water and 20% sodium chloride. If that's the case, then the the reverse. Let's say it's 100% water and no sodium chloride. As a result of that, the water is going to continuously flow into the cell until the cell actually ruptures, leading to what's called cell lysis. Okay, cell breaking. So extreme cytolysis can lead to lysis. All right. Um, you know what? This has already gone. This screencast has already gone for 15 minutes. So I'm actually going to stop now, and perhaps I will cover more of this stuff tomorrow in class. Yeah, I'll have to try to get it in tomorrow's class. Okay, bye, y'all.